So today we're going to learn about the differentiation formula and also where this differentiation formula comes from via first principles. But the first thing to stress is that you can differentiate. Even if you don't understand the first principles stuff, you can differentiate using the differentiation formula, which states that if y equals ax to the n, where a and n are constants, then dy over dx equals nax to the n minus 1. This is our key formula. You can do this, you can apply this. It doesn't matter about first principles, you can do this. So don't let the first principles scare you off, okay? Now the reason we differentiate is in order to find the gradient function. So the gradient function. Now the reason why we use differentiation is because if we look at, say, a curve, unlike a straight line graph like y equals 2x plus, say, 4, where you know the gradient is always 2 along that line, actually on this graph, y equals x squared, our gradient is changing all the time along the curve. It is not constant at all, which is why we need to know the gradient function in order for us to say what the gradient is at any point. And let's remember what the gradient actually represents. The gradient represents rate of change. So if it was a distance time graph, our gradient would represent speed. Okay? So it's very important, the rate of change. So if I was to tell you straight away using this formula up here that we could differentiate this then, so here my a must be 1 and my n must be 2. So dy over dx means the change in y over the change in x, just like when you were finding your gradient m1 equals y2 minus y1 over x2 minus x1 in your straight line graphs and your coordinate geometry. The same sort of thing is meant here with this dy over dx, the change in y over change in x, and dy over dx is the notation used to express that. So by the rule, it says dy over dx equals n, which is 2, times a, which is 1, x to the whatever n was minus 1 power, so 2 minus 1. So actually dy over dx equals 2 times x. So if I pick a value x equals 1 and put that in, at x equals 1, dy over dx equals 2 times 1 equals 2. So at this point, the gradient dy over dx equals 2. Now if I pick the point x equals 8, you'll see that actually at x equals 8, dy over dx equals 2 times 8, which is 16. So at this point, dy over dx equals 16. So you see the gradient is not constant on a curve, which is the whole point of differentiation, to find the gradient function, because it is not constant. Now we can learn where this differentiation formula comes up. But just to show you how we can use it to differentiate multiple terms. So if I had y equals a half x to the 3 over 2 plus 3x squared minus 4x to the minus 2, for instance, which looks nasty. And by the way, as a side point, you must be very good at rearranging indices. You need to get numbers into the form of a number and x to the power of something. We can't have, say, 4x divided by x squared, etc. to differentiate at this point, okay? You need to get it in the form of ax to the n, okay? Or a collection of that, so y equals ax to the n plus bx to the n, whatever, okay? So, y equals this, so therefore dy over dx equals here, if I take it term by term, a is 1 over 2, and n is 3 over 2, so I have a half times 3 over 2 x 3 over 2 minus 1 in the power, and let's do this one, plus 3 times the n comes down, 2, x to the power of 2 minus 1, minus 4 is a, times our n, minus 2, x to the power of minus 2 minus 1. Okay, so if I simplify this up, I get dy over dx equals 3 over 4 x, 3 over 2 minus 1 is a half, plus 6x, 2 minus 1 is just 1, minus 4 times minus 2 is plus 8x to the minus 2 minus 1, so that's minus 3. So there we go, there's a little example of how we differentiate. And just to make ultra clear, if I had something like y equals 20x plus 10, what's going to happen is when we use this formula, anything which is just a number without an x is going to disappear once we differentiate. And a number connect to just x by itself with no power attached to it, because of course this is x to the power of 1, when we differentiate, the number is just going to remain. So let's see how this works. So if we have dy over dx equals, remember here, a is 20, so I've got 20. The power 1 comes down is 1 times x to the 1 minus 1. And curiously, if I show you this one here, x is 10, this is the same as y equals 20x to the power of 1 plus 10 times x to the 0, because remember, anything to the power of 0 is 1, so even a million to the power of 0 will equal 1, okay? So if we look at it that way, because remember everything has to be in the form of ax to the n in this case is 0. So if I'm looking back here, I have a is 10, my power here is 0, that's going to come down, and I have x to the power of 0 minus 1. So if I simplify this up, I have 20 times x to the power of 0, as we already said, x to the 0 is just 1, so it's just 20. And here I have 0 times 10 times x to the minus 1, so anything times 0 is just going to disappear, so that's just 0, isn't it? So dy over dx, as I said before, is just 20, the number without the x. And in another video, you'll sort of see why this comes in handy in terms of finding the tangents and normals to a curve at a point. That is why another use of differentiation, to find the gradient at a point, which then you can find the equation of the tangent and the normal at that point on the curve. But let's now see where this differentiation formula comes from in the form of first, principle differentiation from first principles. And this you'll see in the next video, labeled differentiation from first principles.